So I've actually made this, okay, so that we can draw the cross dot diagram, mention about the shape, okay, we can actually mention the name and so on, the polarity and so on. So the Cl2, okay, this is the cross dot diagram, okay, the shape, okay, if I just do it in form of diagram, this is going to be the shape. The name of the shape, Sharon, can you tell me the name of the shape?
Linear.
Okay. And can you mention also the bond angle? So this one is linear with
180 degree.
okay, 180. So let's talk about the polarity. Okay, is it polar or non-polar, Jeffrey?
Non-polar.
Okay, so it's non-polar. And let's actually look at the intermolecular forces. The intermolecular forces between Cl2 and Cl2. Okay, so what can you say about the intermolecular forces, Giuliano? Non-polar and non-polar.
Van der Waals.
Yes. So van der Waals forces. Okay, van der Waals forces will be intermolecular forces for that. Okay, let's actually go on for HCl. I will draw for you. Okay, H. Okay, this is going to be the structure for HCl. Okay, the cross dot diagram, cross and dot diagram. And then let's actually have a look at the shape. Okay, generally it's supposed to be something like this. Okay, when I draw the shape. Okay, so the name of the shape, again, you can see is linear. Okay, there's no lone pair. Okay, therefore it's going to be 180 degrees. So I want to actually identify whether it's polar or non-polar. Okay, can Benedict, can you actually tell me whether it's polar or non-polar?
Polar.
Okay, it's polar. Okay, if HCl, can you tell me which one is going to be delta negative over here?
Delta negative is chlorine.
Yeah, so this one will become delta negative, delta positive, so it's going to be polar. And then the intermolecular forces for polar and polar.
Is it
Yeah,
is it dipole?
yeah, so it's supposed to be permanent. Okay, permanent dipole, dipole. Okay, and do remember, okay, van der Waals forces applies for all molecules. Okay, therefore, okay, this one also have VDW, but the prominent, okay, or the major forces of attraction is going to be permanent dipole, dipole. Okay, I'll put it over there. Now, CO2, okay, CO2 will be, okay, if I don't want to actually keep on drawing the circle. In your exam, you have to actually draw the circle. For in this case, I will just put it like this. So double bond. Six electrons, six valence electron. Okay, this is the shape. If I put it like this, okay, this will look like this. And can someone tell me, Josh, can you tell me what is the name of the shape and bond angle?
Linear, 180 degrees.
Yeah, good. Okay, and then the polarity, can you tell whether this is polar or non-polar?
It's non-polar.
Okay, can you tell me why it's non-polar?
Because it's canceling each other out.
Yeah, what is canceling each other out?
The bond of OC and CO.
That is not the term that you're supposed to use, yeah, Josh. So please actually do remember, this one applies for everyone. Okay, when you mention it cancels out, yes, you need to be, you need to mention what is being canceled out. So in this case, this one, okay, you have this bond is polar. So you are going to create some kind of a dipole over here. So that arrow over here, it is called dipole moment. So what happens over here is, okay, the dipole moment Okay, dipole moments cancel each other out. So I want you to actually mention about the dipole moment. Okay, that's the term that we need to use. Okay, the dipole moment cancel each other. Okay, and then what is going to be the prominent, okay, forces of attraction? So this one is going to be non-polar. Okay, so Michael, what is going to be the forces of attraction? Yeah, it's only van der Waals forces. Okay, let's move on. Okay, H2O, okay, oxygen. Oxygen is going to be group 16, 6 valence electron. So you have, okay, one H over here. So they will share. So 2 electrons is being used. So another 2 electrons will be the lone pair. So if I put it in this way, lone pair of electrons, some books, they actually put something like this to show the lone pair, still the same, okay? And then you have H and H over here. So this one, okay, the shape, okay, there are 3 names for this, okay, can maybe let me select one person. Megan, can you tell me the 3 names available for this shape for water?
Band,
Okay,
V shape, and forgot the other one.
then V shape. Another one, something to do with linear. We call it what?
Planar, non-linear.
Okay, it's supposed to be non-linear. Yeah. So I will suggest to actually use this term band. Okay, but if you want to use some other terms, yes. Okay, all these terms are inside your syllabus. Okay, so you can actually give all 3. Any of these 3. Yeah, any of these 3. The bond angle. Okay, Nicholas Chai, can you give me the bond angle for water?
104.5.
Okay, very good, 104.5 degrees. So I want to know whether this one is going to be polar or non-polar. Is this polar or non-polar, Jasmine?
Polar.
Okay, so the delta negative towards where?
Towards the oxygen.
Okay, delta negative, so this one delta positive, so it's polar. So polar, okay, so what kind of intermolecular bonding that we expect between water and water? Sharon?
Hydrogen and the permanent
Okay,
induced.
actually for this one, okay, for this one, when we say polar and polar, so we know that it's supposed to have a permanent dipole-dipole. But since it's actually water, okay, where it involves hydrogen with oxygen, so the permanent dipole-dipole that we meant is a special type of permanent dipole-dipole. So it's enough to just mention hydrogen bonding, because this hydrogen bonding is permanent dipole-dipole, okay? But do remember that is the prominent, okay? But do remember they also have van der Waals forces. So the prominent one is the hydrogen bonding. Okay, so no need to mention permanent dipole-dipole, okay? No need. So H2S, sulfur is going to be group 16. Okay, so you have H and H. So you have something like this. So group 16, so you need to have 6 valence electrons. So remaining 4 electrons I put like this. So it will just follow the same shape as water. So this thing will be the same, band, V shape, non-linear. Bond angle is also going to be the same, 104.5. Okay, so this one S and H, and do remember sulfur compared to hydrogen. Hydrogen is the least electronegative. Okay, so sulfur will be the delta negative over there. So therefore they are polar. Okay, so when we look at polar molecules, we just remember permanent dipole-dipole, but it is important to identify whether they have hydrogen bonding. This one involving sulfur, hydrogen bonding is hydrogen with NOF. Okay, therefore there is no hydrogen bonding. So I write down permanent dipole-dipole. Okay, and then do remember all molecules, they have van der Waals forces, but the prominent will be the permanent dipole-dipole. So next, SiCl4 group 14. Okay, so just 4 bonding pair. Okay, and then if I draw Si, Cl over here, Cl here, if you want to show a 3D diagram involving shape of tetrahedral, so it's supposed to be something like coming over here, another one dotted line over there. Okay, so the shape over here is, Nathan, can you give me the shape?
The shape, sir.
Of SiCl2, SiCl4?
Tetrahedral.
Yeah, tetrahedral. And what is going to be the bond angle? Thompson, what is the bond angle? 109.5. Yeah, 109.5. And then if I want to show whether they are polar or non-polar, okay, do remember, okay, even though the bond is polar, okay, the dipole moment, okay, the dipole moment will cancel each other out. In this case, if you compare silicon and Cl, Cl is more electronegative. They will pull this side. But because it's symmetrical, okay, the dipole moment will cancel each other out. So it will become non-polar. Okay, so SiCl4 is non-polar molecule. So Michelle V, can you tell me what is the prominent intermolecular forces for this?
Van der Waals.
Yeah, van der Waals. Okay, another two. Yeah, PCl3, phosphorus is group 15. Okay, so they have one lone pair. It's a bit messy, but it's okay. Okay, I just want to show this one will look like this. Cl coming out, Cl dotted Cl, similar to ammonia. Okay, so the shape, okay, similar to ammonia. Ryan, what can you say about the shape?
Pyramidal.
Okay, very good, pyramidal. And what is the bond angle?
107.
Yes, okay, similar to ammonia. Yeah. So here, okay, if it is going to be the moment we see this molecule is not symmetry, okay, not symmetrical, okay, so we can say that, okay, compared to phosphorus and Cl, okay, which one is more electronegative? Ryan, which one do you think more electronegative?
Chlorine.
Yeah, because, okay, chlorine is actually at the right hand corner of the periodic table. Okay, so you can actually use the method that I taught you. Okay, when you go across the periodic table, okay, the electronegativity increases, down electronegativity decreases. Okay, please actually remember that. So here the delta negative will be towards the chloride. Okay, so here it's going to be definitely polar. Okay, because of the lone pair also. Okay, it makes it non-symmetrical. So if it is polar, then what type of bonding that we are going to expect, Frederick? Intermolecular bonding.
Permanent.
Yeah, permanent dipole. So do you think that it has hydrogen bonding?
No.
No. Okay, so permanent dipole. So this one will be W.
Sir.
Yeah.
If the chlorine ions are the ones that are electronegative, but then there's the lone electron, lone pair of electrons on the phosphorus. Won't they cancel each other out?
Not fully. They will still cancel, but not fully. Like for example,
So
because
then,
we just want, imagine like this. Okay, imagine we are looking at this situation. You have a girl, okay, and then 3 people are pulling this side, okay, and then there is lone pair of electrons. So we just want to see whatever that lone pair over here, bonding pair, okay, whether there is going to be going somewhere or not. So imagine that you are pulling over here, the electron will go here, okay, but there is still electron over there. Okay, there's still going to be electron over there. So is that going to be cancelled out fully? It's not. The resultant forces that you have over here is not the same as the resultant forces being cancelled over there. So it's not going to be cancelled fully. Just imagine like if you have carbon and then you have fluorine over here, Cl, Cl, Cl. Imagine this is going to pull the electron with different strength, and this one are pulling with different strength. So of course the electron are not going to be equally distributed. So our concern over here is not to identify where the electron might be. Our concern is I just want to find out whether the electrons are equally distributed throughout the molecule. So once I know that there is going to be a lone pair and then there is going to be something like this, whatever, let's say H over here, I know that, okay, this one, the electron will go towards nitrogen. So I know that this part is going to be delta negative. But if you have PCl3, okay, what happens is P will be here, lone pair here, Cl, Cl, Cl. Even though they're trying to pull over here, it will not be cancelled equally because it's not symmetric. So there will be still possibilities of the electrons to be somewhere. I think highly possibility will be the lower part will be delta negative. Okay, because three forces being pulling it down. Is that okay, Christopher?
Yeah, like
Yeah.
although is the dative bond strong, like the electronegative
if you're talking
things
about dative bond, yeah,
pair of electron.
yeah. If you're talking about dative bond, okay, then it's going to be different. Okay, then it's going to be
No,
different. Like for example, if you're talking about ammonium ion, then you have hydrogen, 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 and then this one shared to this hydrogen. So this one is ammonia. So whether do I actually when it comes to ammonium ion, can I say that this ammonium ion polar or non-polar? Okay, in this case, okay, because they are going to be all the like some sort of a, it's going to be some sort of cancel with each other. Okay, then you can say it's going to be non-polar. But do remember, this one is ion. Okay, so normally they will not ask whether ion is polar or non-polar. Okay, because we are more interested towards the covalent bond. Okay, but if they ask, then you just follow the same thing. This is symmetry. Okay, if it is symmetry, okay, so we can actually just say it's going to be cancelled out with each other. Still okay. Okay, but when it just alone, then it's actually unequal distribution. Okay, so we just move on. Is it okay, Christopher? Does it answer your question?
So this the distribution that matters, right?
Yes.
Okay.
Distribution matters because I think we no need to actually worry where the polarity goes unless for this worksheet they actually ask us to show. Okay, if you want to show, I think just show one part is delta negative, one part delta positive is still okay. Okay, so here ammonia similar like your constant just now. So if you have N, okay, so you have H, H, H. Okay, since we want the cross dot diagram. Okay, so okay, so you will have nitrogen and then H, H, then H. Sorry, I will draw it like this. Nitrogen 1 like this one H, dotted line to H. This one is to show, okay, it's going to be a 3D diagram. Okay, so I don't use the same lines. Okay, so here the shape is going to be pyramidal, similar like just now, pyramidal, 107 degrees. Okay, so this one, whether it's polar or non-polar, you can actually just confirm over here. Okay, the nitrogen is more electronegative, so it will go there. Delta negative, delta positive, so it's polar. Okay, but it's important. Okay, when a polar molecule, you know it's permanent dipole-dipole, but always double check whether they have hydrogen bonding or not. Okay, so I just want to check whether there is hydrogen bonding or not. Audrey, can you tell us whether there is hydrogen bonding? Audrey, are you there? Yeah. Is there any hydrogen bonding for ammonia?
Yes.
Okay, so there is hydrogen bonding. So the prominent bonding over here, intermolecular bonding, is hydrogen bonding. So this one plus BDW. So this is going to be prominent. Okay, this one is going to be the entire, okay, the solution for this worksheet.